Alright guys, here we are, 0654, paper 4.2 from winter 2019, and we're on question 6. Okay, we're told about dolphins, alright, and we're told about the sound waves that they produce in this frequency 200 Hertz to 130,000 Hertz, and we're then asked what is the audible frequency range for a human. Okay, this is unfortunately something you just need to remember, which is 20 to 20,000 Hertz. I suppose the nice thing here is that the number at the front here is the same, 20 and 20. You're just going from 20 to 20,000. Okay, no other numbers will count here, unfortunately. All right, we're then discussing ultrasound, and the whole idea about ultrasound is basically it's an echo. Okay, dolphin sends out a sound wave which reflects and then comes back. The longer the time it takes to come back, the further away the thing. And actually, it's a proportionality. Okay, we're told a few things in the question, as I've suggested before. Do something which helps you. Okay, so this time I've just drawn a circle around the numbers I'm given, and I've written some symbols next to it. Okay, I've got frequency of 50,000 Hertz. I've got distance here, okay, of 20 meters, and I've got a speed here of 1,500. In the question, we're asked to calculate the time t. All right, so I'm looking at these numbers, and I've got 4 variables here. I only really need 3 of them. I need d, I need v, and I need t. Okay, we know we have this link between the two. Distance is the product of speed and time. Okay, as we've discussed in class, I think probably the easiest thing to do is to put the equation down as multiple form, so distance, speed times time, and then rearrange. So time is distance divided by speed. Now we have to be a bit careful here with the time. You notice here I made a small mistake when I first did it, because I initially took a time of a distance of 20. But remember that what's happening here, just like you might do with sonar on a ship, okay, we are sending a pulse from the top back down to the bottom. So in total, my wave is traveling 20 meters down and then 20 meters up. So the total distance there is actually 2 times 20, 40 meters. Okay, we've got 40 meters divided by the speed of sound in water, and therefore you're getting the 0.026666666. As usual, take it to 3 significant figures, and you've got 0.0267. I think it's even 2 significant figures in the answer scheme. Don't worry, that's not wrong. Okay. We're then not told, to calculate the wavelength, lambda, of ultrasound. And again, you're reminded of the frequency. Okay, very nice of them. Okay, the missing bit of information there is obviously the speed. Well, that is told way back in the beginning. Okay, so sometimes these variables, yeah, they carry on. So just be careful. If you don't know something, it's probably buried in a previous text. V equal F lambda. This holds for all waves. Okay, so even if you're thinking about water waves, sound waves, light waves, you can use that same equation. All right. Again, writing down in product form, V equal to F lambda. I've got my triangle, V, F lambda. I don't want to know V, I want to know lambda. Cover up the lambda, I've got V divided by F. Well, I've got a speed of 1,500 just from the top here. I've got a frequency of 50,000, and I can see that I've got a factor of 5 cancelling out nicely. We have 0.03 meters. Okay. Lastly, this is where we need to keep that equation V equal F lambda in mind here. Lastly, we're asked, what happens if we change the frequency of the sound? Okay, we're going to change the frequency to 100,000 Hertz, and we're being asked to suggest what effect, if any, T here, this will have on the time taken for the pulse to travel to the fish and return. Now, if the time is going to change, yeah, the distance is the same, therefore the speed must change. Now what we know is all sound waves travel at the same speed in any medium. So all sound waves in water have the speed 1,500 meters per second. All sound waves in air have the speed 330 meters per second, which means the time will not change. Okay, there will be no effect. Even if I change the frequency, I will have the same time. Why is that? Well, really it comes from our V equal to F lambda. All right. The speed is constant. If the frequency is going up, then the wavelength is going down. But we're noticing here we've got that caveat that the speed is the same. It does not matter what the frequency is or the wavelength in this sense, the speed will be the same. All right. Suggest a speed of waves through air. Well, I've just mentioned it. Well, I said 330, 340, something like that. In this question, Cambridge were quite nice. Yeah, they basically said anything less than 1,500 meters per second. All right, I've given you this number because it's kind of the established number for the speed of sound in air. Okay, but it's got to be less than 1,500. Why? Well, when we're thinking about sound traveling through a gas, yeah, versus sound traveling through a liquid, water, for example, we've got to think about our particles. In a gas, the particles are further apart. All right, in a gas, they're further apart, so it means there's more time between the collisions, and therefore a slower propagation of the wave through the medium. Okay, in liquids, the particles are closer together, and then in solids they're going to be really close together, and that's why we find the speed of sound in solids incredibly fast. You're talking 5,000 meters per second versus 1,500. All right. We were getting into longitudinal. You may notice this is a very common theme, okay, in CIE's past papers, so please make sure you are well versed in this, okay. We've got longitudinal and transverse. We're asking to describe the differences between longitudinal and transverse waves. 2-mark questions, so not too much, okay, and you are encouraged to draw a diagram. I've done this a few different ways, and I'm coming on to this one as my sort of favorite one. Okay, we've got longitudinal waves and transverse waves. I've split it in half. We've got the wave traveling in the same direction. Yeah. Notice we're using this word propagation. Okay. The question actually does ask you to talk about propagation and vibration. All right. Propagation just means traveling through. Direction of propagation means direction of motion. And the vibration is about the motion of the particles themselves. In longitudinal, we notice we've got propagation from left to right and vibration from right to left and then back again. So we're kind of oscillating in this way. Transverse, again, we have propagation, travel to the right, but vibration up and down. I then explained that in longitudinal waves, the direction of vibration is parallel to the direction of propagation. In transverse waves, the two are perpendicular. Now notice we are not saying, okay, I've said this a few times in class, do not say up and down or left and right for the vibration, yeah? Try and stay away from those phrases because they are too vague, all right? We understand what you mean, but you would lose marks if you were referring to that. Use the words perpendicular and parallel to describe these vibrations. Last one. Room temperature, water is a liquid. The water is cooled sufficiently, it turns ice a solid. Describe the difference between water and ice in terms of forces between the molecules and motion of the molecules. Okay? You need to look at the numbers of marks there, 2 marks. You need a sentence probably for each. All right? I've gone it this way. I've said in ice, we've got forces between the molecules are very strong, and the molecules, if you're unsure, vibrate on the spot. Okay, that is me setting up to then say a comparison between ice and water. In water, the forces are lower than in the solid. All right, they're not lower than in a gas. Okay, and the particles or molecules can move past each other. So I've got a statement about forces. Okay, in each one, and then I've also got a statement about motion in each of my sentences. That's how I would do it. If you wanted to, you could phrase it slightly differently. You could say that the forces are lower in water than they are in ice, and the particles move more freely in water than they do in ice. That would also be fine as well. Different ways of answering each of these questions.